Hi, Tom with Automation Direct here. The following video is a continuation on the subject of motion control. In this standalone video, I will cover using a SureStep Stepper System that is controlled with the built-in high-speed pulse output ability of a DirectLOGIC DL05 programmable logic controller. The stepper motor I use in this video will be applied to the part feeder station. This will be the first stage in an application that utilizes the various motion control solutions offered by Automation Direct. Let's get started. The part feeder station shown in this Learn video is the first stage in a multiple motion control system application. It uses the DirectLOGIC DL05 PLC's built-in high-speed pulse output, referred to as Mode 30, to control a SureStep Stepper System. A CMORE micrographic panel will be used as the operator interface. Included will be various sensors to control the part feeder's operational functions. The part feeder was designed as a mechanism for dispensing 14mm glass marbles and 9/16 inch diameter steel and brass balls, one at a time, from a cylindrical hopper into a polycarbonate tube. For reference, the parts being dispensed are all a little over 1/2 inch in diameter. Looking ahead at future Learn videos on motion control, the second stage of this application will use a SureStep Stepper System controlled with ASCII commands to an advanced microstepping drive, while the third and final stage will be based on Automation Direct's servo system controlled with a high-speed output module installed in a Productivity 3000 programmable automation controller. The topics covered in this video include an explanation of the application and the equipment used to construct the part feeder, setting up the hardware's jumpers and dip switches, programming the DL05 PLC with DirectSoft 5 ladder logic and iBox instructions, using the CMORE micrographic panel, and finally an operational demonstration of the end result. The slides shown in the video can be downloaded as a handout from the Learn website and used to follow along with the video or used as a refresher. Look for the note below the video that mentions takeaway training PDFs and demo projects. For additional information on motion control applications and solutions, please refer to the Automation Notebook article titled Starting with Steppers under the Tech thread, Part 1 of 2, published in Issue 21, Fall of 2011, and Part 2 of 2, published in Issue 22, Spring of 2012. Links to Part 1 and 2 are shown here. The 8-part video series titled Motion Control DirectLOGIC Micro PLC C-Trio Module to SureStep Stepping System with CMORE Micrographic Panel is another excellent resource detailing motion control systems information. A link to the video series is shown here. Next, I will talk about the application and the components that were used to put it all together. The part feeder station was designed to dispense one part at a time from a cylindrical hopper into a polycarbonate tube. The parts are then sequenced to the next station. As mentioned earlier, the parts used in this application consist of 6 different colored glass marbles, steel balls, and brass balls. The parts are all a little over 1/2 inch in diameter, as mentioned before. A slotted polycarbonate disc coupled to an Automation Direct NEMA 17 stepper motor is used to rotate the disc. The slot in the disc allows one part at a time to drop into the slot as it rotates. The part falls into the exit tube when it is rotated over the tube's opening. The part feeder station is built using T-slotted framing. It includes a part hopper, a slotted disc that is driven with a SureStep stepper motor, with the stepper motor coupled to a coil encoder. The encoder provides speed control and jam detection. There is also a fiber optic photoelectric sensor to detect when the exit tube is full, and a capacitive proximity sensor to determine when the part hopper is empty. The electrical controls for the part feeder station are housed in a non-metallic JIC NEMA 4X enclosure. The enclosure has a see-through door window that allows viewing component indicators. The CMORE micrographic panel and master control power start and emergency stop push buttons are mounted through the enclosure's door. Located on the enclosures panel are AutomationDirect's DirectLOGIC DL05 PLC, AccuAmp DC current sensor, Rhino 24-volt DC power supply, which provides 24 volts DC power to the PLC's DC inputs and also power to the AccuAmp, and the master control power circuitry relay. The SureStep stepper motor drive and power supply are also mounted to the enclosures panel, along with terminal blocks, wire duct, and DIN rail. Machine tool wire is used to interconnect all the devices. AutomationDirect multi-wire connectors and multi-conductor flexible control cable is used to connect the control panel enclosure to the part feeder station. Schematic diagrams have been created that were used to wire the controls for the part feeder station and control panel. Shown here is the first schematic diagram showing the power circuitry. The master control circuitry, power on push button, and emergency stop push button are included. The ADC Rhino 24-volt DC power supply used to provide power to the PLC's DC inputs and power to the AccuAmp DC current sensor is also shown. The second schematic diagram includes the DirectLOGIC DL05 PLC, SureStep Stepper System motor, power supply and drive, coil incremental encoder, AccuAmp DC current sensor, 4 to 20 milliamp analog current input module, the CMORE micrographic panel, and both the fiber optic, photoelectric, and capacitive proximity sensors. Different colored machine tool wire from AutomationDirect was used for the various conductors to help identify individual circuits. The AccuAmp DC current sensor is used to detect if the part feeder is jammed. This is accomplished by monitoring the current from the stepper motor power supply that powers the stepper motor drive. The 4 to 20 milliamp signal from the DCT100-42-24-F AccuAmp DC current sensor is wired into channel 1 of the F0-0480-1 analog current input module located in the DL05 PLC's expansion slot. The position of jumper J3 on the analog current input module determines the input signal level, either 4 to 20 milliamps or 0 to 20 milliamps. I set the jumper not connecting the two pins as shown in the diagram, which allows an input signal of 4 to 20 milliamps. Shown here is a block diagram of the part number STP-DRV-6575 micro-stepping drive used in my application, and a list of the main features that can be gained by using the drive in your application. The STP-DRV-6575 micro-stepping drive is wired using the two separate pluggable screw terminal connectors as shown here. The power connections for the supplied DC power and the stepper motor lead share a 6-position connector. The digital inputs and one output signal share an 8-position connector. Also shown in the diagram are the status LEDs, the rotary switch used to select the stepper motor based on either its part number or current rating, and the 8-position dip switch used to select the driver's operating parameters. The stepper motor that is used with the STP-MTR-6575 drive is selected based on its current rating by using the rotor switch and choosing the position from the table. In my application, I have used a SureStep stepper motor part number STP-MTR-17060D with a 2.0 amp current rating, so the rotary switch is set to position 8. The two internal jumpers on the STP-DRV-6575 drive typically do not need to be changed from the factory defaults. The S3 jumper is used to set the step pulse type. In my application, I am using Step and Direction, so I keep the factory default with jumper S3 in the 1-2 position. The S4 jumper is used to set the step pulse noise filter. The noise filter is used to prevent position errors caused by electrical noise on the command signals. I choose the factory default setting with the S4 jumper in the 1-3 position. If there is need to change either jumper, then the stepper drive cover needs to be removed. The 8-position dip switch is used to set up the stepper drive's parameters. Dip switch positions 1 and 2 are used to reduce the drive's power consumption, which also reduces the amount of heat generated. This is done by limiting the motor running current by a factor of 80 or 90%. The current reduction can also be set for 100% without limiting the current to the motor. The current should be increased by a factor of 120% when using the micro-stepping feature of the drive, which is one of the available settings. Keep in mind that the torque is reduced or increased by the same amount as the percentage factor. Stepper motor systems have a tendency to resonate at certain speeds. To improve the motor's performance by reducing this resonation, dip switch 3 is used to select how strong the anti-resonance and dampening control algorithm is applied. The motor and load inertia range can be set to either 0 to 4 times or 5 to 10 times. Dip switch 4 can be used to reduce the power consumption and lower heat generation by limiting motor idle current to either 90% or 50% of the running current. Keep in mind the holding torque is reduced by the same percentage. The step resolution and steps per revolution is handled by dip switch positions 5, 6, and 7. The available choices are 20,000, 12,800, 5,000, 2,000, 400 smooth, 400, 200 smooth, or 200 steps per revolution. Dip switch position 8 is the self-test function. When position 8 is in the on position, the motor automatically rotates back and forth 2 turns in each direction. This feature is used to confirm that the motor is operational. For the application in this video, the drive dip switch is set up for a current reduction of 80%, a load inertia of 0 to 4 times, an idle current reduction of 50%, a step resolution of 400 steps per revolution with smooth operation, and the self-test is left off. There are 2 LED indicators on the STP-DRV-6575 drive that are used to indicate if the drive is operating correctly or if there is a problem. In the event of a drive fault or alarm, the green LED will flash 1 or 2 times, followed by a series of red flashes. The pattern repeats until the alarm condition is cleared. Use the table shown here to determine the cause of the fault or alarm. The first step I'll do in programming the DirectSoft 5 ladder logic for the DL05 PLC is to set up the parameters for the high-speed mode 30 pulse output. To assign mode 30, I'll start by loading a constant value of 30 typed in as K30 into the accumulator and then output it to the vMemory register V7633, which is the dedicated location for the mode select register in the DL05 PLC. Next, I'll set up the profile parameter table to start at vMemory address V2320 by loading octal address 02320 into the profile table pointer at vMemory address V7630. I will be using the Y0 and Y1 outputs for my pulse and direction signals respectively to the stepper motor drive, so I'll load the constant 103 into the accumulator and then output the value to the physical I/O configuration vMemory address V7637. Finally, I'll set up no filtering for inputs X1 and X2 by loading constant 0 into the accumulator and outputting to vMemory address V7635 and V7636. I continue setting up the parameters for mode 30 in the second ladder logic rung shown here. I load the constant 2000 into the accumulator and output it to the first vMemory address V2320 for the profile parameter table, which selects a velocity profile move. I next load a double word constant value of 80000000 into the accumulator and then output it to the direction select vMemory address V2321, V2322 to set up a counterclockwise direction for the velocity profile move that I will execute later. The last parameter I set up is for the initial velocity I want the stepper motor to run. I load the constant value 10 into the accumulator and output it to the velocity vMemory address V2323 in the profile parameter table. This value is multiplied by a factor of 10 to produce an initial velocity of 100 pulses per second. In the third rung, I program the cycle control latch circuit. This circuit is controlled by the F1 and F2 function keys on the CMORE micrographic panel. F1 is assigned to the PLC's internal relay C2 as the stop push button, and F2 controls internal relay C3 used as the start push button. The internal cycle control relay C4 is latched in through a C4 normally open contact. I also program a bit of word output as V2010.2, which is bit 2 of vMemory address V2010 that I assigned in the CMORE Micrographics panel's function object LED control word as tag name in run, which controls the F3 LED anytime the part feeder is in run mode. The part feeder station uses various sensors to control its operation by detecting the presence of the parts, both the colored marbles and the metallic spheres in my application. A timer, T0, is used with the hopper anti-capacitive sensor to allow the rotary slotted disc to continue to run for 10 seconds after no parts are detected. This allows any additional parts in the hopper to keep moving, detected, and the timer reset. The purpose is to remove as many parts from the hopper as possible. There is a tube that the parts fall into at the exit of the slotted disc. Because of the potential for the parts to back up to the rotating slotted disc and cause a jam, a fiber optic photoelectric sensor monitors the exit tube just below where the parts are dropped from the slotted disc. The parts interrupt the photoelectric sensor as they fall for a split second, but if the parts back up, the sensor is kept blocked. Because we would not want the run mode to pause every time a part exits, a second timer, T1, is used to not pause unless the backed up part interrupts the photoelectric beam for more than 1 second. The actual velocity profile move is executed by enabling the internal Y0 signal. In my case, I use the cycle control contact C4 along with a couple other conditions to enable Y0 as shown here in ladder logic rung 6. The other conditions that control the step drive run include exit tube not being full, timer T1, the hopper not empty, timer T0, and the stepper motor motion not detecting, no step motion. Let me point out that the velocity parameter stored in vMemory address V2323 can be changed on the fly. With a pulse encoder coupled to the stepper motor, I have the ability using the encoder's once a revolution Z channel marker pulse to sense the position of the slot on the rotary disc. This allows me to increase the speed of the rotary disc once it clears the drop point, count the A-channel pulses that are produced at 100 per revolution, and just before the slot gets back to the drop point, decrease the speed to allow time for the part to drop through the exit tube. The ability to change speeds from slow to fast and back will increase the parts that can be produced. In rung 8, I have used an up-down counter, CT0, to count the encoder's A-channel pulses. This is done through the PLC's input X3, but only when the fast-speed C1 signal is active. I use a count preset of 85 to allow the rotary slotted disc to stay in fast speed for the majority of each rotation of the disc. Once the count preset is reached, the counter's contact, designated as CT0, is actuated. This drops out the fast-speed C1 latch relay circuit and also resets the up-down counter so it is ready for the next rotational cycle. The encoder produces 100 pulses per revolution, so fast speed is active for 85% of the rotation, or approximately 360 degrees of rotation. The slot in the rotary disc is presented over the drop point during slow speed for approximately 54 degrees of rotation. Of course, the amount of rotation for both fast and slow speed can be adjusted by changing the count preset. The following two ladder logic rungs select either the slow speed at 100 pulses per second or the fast speed at 300 pulses per second based on the state of the fast speed internal relay C1. This is accomplished by loading different constant values into the velocity vMemory address V2323. I use an AccuAmp DC sensor to monitor the current between the stepper motor power supply and the stepper motor drive. The current sensor produces a 4 to 20 milliamp signal that is proportional to the DC current flowing through the sensor's window. I wire the AccuAmp's output signal into channel 1 of an analog current input module located in the open slot of the DL05 PLC. I program an iBox instruction labeled Analog Input Module Pointer Setup to configure the F0-04AD-1 analog current input module as shown here. The base number is a constant 0 with the default slot number as constant 0. I designate the number of input channels as constant 4 and decide on using binary for the input data format by assigning a constant 1 to this parameter. I use vMemory address V2000 as the starting location for the input data address. Now that I have a means to measure the current being used by the stepper motor, I can use the measurement to compare it to a set point and determine if the running current goes over the established set point value. Here I program a greater than or equal to contact to compare the driver current to my overcurrent set point. If the running current becomes greater than or equal to the set point value, the jam internal relay C5 will energize. The jam signal is used in the next rung as a one-shot to latch in the reverse rotation circuit. In rung 13, I look for the jam condition signal, which indicates the possibility of the part feeder being jammed, and I use the signal as a one-shot to latch the jam detected internal relay C6. At the same time, I start my jam timer T2, which will keep the circuit latched in for the 10 seconds I have programmed. The reverse rotation circuit will be reset when the jam timer times out. The next two rungs shown here are used to reverse the direction of the stepper motor on the fly. This is accomplished by changing the double word value in the direction select vMemory address V2321 V2322 located in the profile parameter table. The normal clockwise direction is selected with a constant 80000000 loaded into V2321 V2322, and counterclockwise is selected with a constant of 0 loaded into V2321 V2322. The last area of the ladder logic program includes a circuit to detect no motion from the stepper motor based on missing encoder pulses. The encoder produces 100 pulses per revolution, as I mentioned before. I decided to use the encoder's B channel that is wired into the PLC's X4 input, although I could just as easily have used the A channel that was used for the fast-slow speed feature. The pulses from the encoder are used to continuously reset the motion timer T3 anytime the step drive run signal is true. As long as the T3 timer keeps getting a reset signal within 0.2 of a second, it never times out. If the timer fails to reset, it will time out and initiate the latch circuit shown in the next rung. The last rung shown is used to latch in the no step motion condition internal relay C7. It is triggered by the motion timer T3 timing out. The no step motion signal will stop the step drive run Y0 output shown in rung 6 and also activate an alarm on the CMORE micrographic panel with the message slotted disk jammed and the F1 function key LED blinking. The no step motion alarm latch is reset by pressing the cycle stop push button on the CMORE micrographic panel and taking the part feeder out of cycle control, internal relay C4. A complete documented copy of the DirectSoft 5 project file for this application can be downloaded from the Learn website. Look for the note below the video that mentions takeaway training PDFs and demo projects. For simplicity, the CMORE micrographic panel used for the application consists of just one screen. The part feeder is started and stopped from the CMORE panel using the F1 and F2 function keys. Indicators are used to show the part feeder in either run or off mode. The stepper motor speed is displayed on the panel, and also the amperage to the stepper motor is displayed. The ability to adjust the overcurrent set point is done with a numeric entry object on the same panel screen using function keys F4 for increment and F5 for decrement. There are also indicators showing the status of the exit tube full and hopper empty sensors. This video does not cover detailed programming of the CMORE micrographic panel, but a complete copy of the CMORE project file for this application can be downloaded from the Learn website. Look for the note below the video that mentions takeaway training PDFs and demo projects. Next, I will demonstrate the operation of the part feeder station. Normal operation is with the slotted disc rotating in the counterclockwise direction when viewed from above. The encoder's Z channel triggers the stepper motor to change from slow to fast speed when the slot is just past the drop-off location. The drop-off location is the exit hole that feeds the part to the exit tube. The encoder's A channel pulses are counted up to a total of 85, representing 85 out of the 100 pulses per revolution, or a little over 300 degrees of rotation. When the preset count is completed, the stepper motor speed reverts back to the slow speed. The ability to run at the fast speed during most of each rotation and then slowing down just over the drop-off point allows a larger output of parts per minute. Here I demonstrate how the exit tube full fiber optic photoelectric sensor works. I block the parts from exiting the exit tube until such time as they back up to the photoelectric sensor. In the ladder logic, as I explained earlier, is a timer that starts any time the photoelectric sensor is actuated. As soon as the timer times out, the stepper motor execution is halted. It will stay halted until the photoelectric sensor is no longer blocked, as seen here. Whenever the hopper empty capacitive sensor, which is mounted to the part hopper, no longer detects any parts in front of it, a 10-second timer is started. The slotted disc continues to rotate. The intention is to keep any parts that haven't been removed from the hopper to be detected by the hopper empty sensor. If no parts are detected, the timer will time out as seen here, and rotation of the slotted disc is paused. The rotation will pick up again if additional parts are placed in the hopper like this. The purpose of using the capacitive sensor is to both empty out as many of the parts as possible, although in most cases a few will remain, and also the operator can be alerted that more parts need to be added to the hopper. The AccuAmp is used to monitor the current from the stepper motor power supply to the stepper drive while the stepper motor is running. If the running current climbs above the set point that is entered on the CMORE panel, then the condition is latched in through a timing circuit for 10 seconds, which causes the stepper motor to change direction, rotating clockwise for the duration of the 10-second timer, and then the rotation reverts back to the normal counterclockwise direction. I can demonstrate an overload condition by using my hand to put slight pressure on the parts as shown here. The purpose of reversing direction under an overload situation is assuming that there is some sort of jam in either the hopper or at the exit tube, and by reversing direction, the jam will be cleared. I should point out that the fast-slow speed circuit based on the encoder's Z-channel marker pulse does not work the same while in the reverse direction, although parts are still able to be dropped at the exit tube. The last feature I will demonstrate, which is built into the design of the part feeder, is the ability to detect no motion. This is accomplished when the stepper motor is running by using the encoder's B-channel pulses to continuously reset timer T3, which prevents the timer from timing out. Timer T3 has a preset of 0.2 seconds. The encoder provides 100 pulses per revolution, which easily keeps the timer in a reset condition. If the stepper motor stalls or stops rotating for any reason, then timer T3 will time out and latch into the no-step motion circuit. When the no-step motion circuit is actuated, an alarm message appears on the CMORE panel. I can demonstrate this action by removing the power to the stepper motor power supply. As can be seen here, the CMORE beeps and displays the alarm message slotted disc jammed while the background screen flashes between red and normal. To reset the alarm, I need to take the cycle control circuit out of the run mode. After determining and clearing the jam, I can place the part feeder back into the normal run mode as shown here. That wraps it up for this Learn video covering motion control. Hope you found it informative, and thank you kindly for watching. Please look for the next series of Learn videos that continue on the subject of motion control.